We know that Routh-Harwich criteria is a mathematical procedure to find how many roots of the characteristic equation are having positive real part, negative real part or zero real part. Or when it comes to the control systems, how many closed loop poles are lying in left of the S-plane, right of the S-plane or on imaginary axis. So we will know the number of poles in left of the S-plane, right of the S-plane, imaginary axis, but we cannot find the exact location of the poles, especially left of the S-plane or right of the S-plane. And again, we don't know whether the poles are real or complex. Let us say there are two poles lying in left of the S-plane. Those two poles can be either real or complex. So that information also we cannot find out. So we can say that the Routh-Harwich criteria is used to find the absolute stability of the system. Means I can say only one word answer whether it's stable or not. So, but whether it is more stable, less stable, this information which is not available with the Routh-Harwich criteria. This is one of the limitations of Routh-Harwich criteria. But to overcome this, we can change the imaginary axis from s is equal to 0 to s is equal to any other value. So this way we can find out the relative stability of the system. So what is relative stability? Let us look at these two examples. I have three poles for this particular system. Let us say system is A. So in this system I have a pole which is very nearer to the imaginary axis and two complex poles are away from it. Now when you look at the other B system, I am having pole away from the real pole, away from the imaginary, and again other two poles away from the imaginary. When you look at these two, A system having a pole nearer to the imaginary, which means whenever there is some change in the gain values or whenever there is some change in the parameters in the system, there is a possibility of this pole is moving slightly towards the right and it may cross the imaginary axis, so it may jump into the unstable region. That means this system is less stable, and whereas here, so here also we have possibility, but the variation of gain is large. So until otherwise you vary the gain largely, this pole cannot be moved towards the right direction. Therefore, as long as the poles are away from the imaginary axis, we say the system is more stable. When the poles are close to the imaginary, we say system is less stable. So what is your Routh-Harwich criteria? Right, Routh-Harwich criteria will give you there are three poles in the left of the S-plane. So here I have three poles, here I have three poles. Therefore, we cannot find out the relative stability. So RH criteria cannot give you so which is more stable, which is less stable. Now the solution for this is one way. So here let us take your S-plane. So in this S-plane, the same example I am taking, I have one pole, another pole, three poles are there. Now s is equal to 0 is axis, imaginary axis. I can change this imaginary axis from s is equal to 0 to s is equal to minus sigma, and sigma is the distance from origin to this place. So what I can do now, let us say when s is equal to 0, normally we can form the Routh array, then you can find out how many poles in left of the S-plane. So for this example, you will be getting three poles in left of the S-plane, therefore no sign changes in the system. What I can do is, so when you shift this imaginary axis from s is equal to 0 to s is equal to minus sigma, then take another parameter z, then substitute s is equal to z minus sigma, wherever s is there substitute z minus sigma, then get the new characteristic equation. And for that new characteristic equation, you form Routh array and find out sign changes. So even if there are no sign changes, which means whatever the sigma you are taking, so in that region also you don't have any poles. We know that from s is equal to 0 to right of the S-plane there are no poles, and from s is equal to minus sigma to right side there are no poles, and all the poles will be left off of this plane. So this axis can be slowly moved like this, then we can find out where there are one or two poles lying in right of the s is equal to minus sigma plane. So this way we can find out the relative stability using Routh-Harwich criteria. So to understand this concept, let us illustrate one example. So the example is like this, the problem statement. Check whether all the roots of the characteristic equation s cube plus 7s square plus 25s plus 39 is equal to 0 have real parts more negative than minus 1. Characteristic equation is given to us, then we need to find real part rules having a real part more negative than minus 1. What do you mean by more negative than minus 1? More negative than minus 1 is minus 2, minus 3, minus 4 like that. So how many are there like that? So it directly tells you that how many poles that are there left off of the s is equal to minus 1 axis. So I have s is equal to minus 1 axis. You find out how many poles which are there in left off of this particular axis, right? So first of all, we'll see whether the system is stable or not. That means in this system there are 3 poles. The highest degree is 3. There are 3 poles. Those 3 poles in the left of the S plane or right of the S plane. First of all, we'll find that. So we can simply form Routh array. So s cube, s square, s power 1, s power 0, 1, 7, 25, 9. And this will be 25 minus 39 by 7, which will give you 19.42, and this 39 is carried forward here. Then you look at the first column, you have 1, 7, 19.4 and I have 39. Therefore all are positive, therefore there are no sign changes, which means all 3 poles are lying in left half of the S plane, that is when the axis s is equal to 0. The next case, we substitute s is equal to z minus 1. And wherever s is there we replace z minus 1, therefore it gives us z minus 1 whole cube plus 7 into z minus 1 whole square plus 25 into z minus 1 plus 39 is equal to 0. Then if you simplify, you will be getting the new characteristic equation in terms of z, that is your z cube plus 4z square plus 14z plus 20 is equal to 0. So this again I can form Routh array. What are the elements? 1, 4 and 14 and 20. Then this is nothing but you have 14 minus 20 by 4, that gives us 9, and this 20 carry forward here, that is 20. What are the first column elements now? 1, 4, 9, 20. So these are the first column elements and all are positive values. So there are no sign changes. So even if you replace s with the z, a new axis s is equal to minus 1, still I am getting no sign changes, which means all 3 poles are lying in left half of the plane having s is equal to minus 1, or you can say all the roots of the characteristic equation are having a real part more negative than minus 1. So this way we can find the relative stability of the system using RH criteria.